You can't access those websites in a regular browser, you have to do so while connected to the Onion router. This world of quantum computing has always intrigued and captivated the imaginations of scientists and engineers alike. For decades, the field has been shrouded in mystery and immense potential. It promised a revolutionary future, one where we could solve some of the world's most complex problems, problems that are simply beyond the reach of classical computers. From breaking encryption to simulating complex molecules and advancing artificial intelligence, the possibilities seemed endless. But recently, something unexpected shook the quantum world. Microsoft, one of the largest and most influential tech giants globally, made an announcement that sent shockwaves through the tech community. They had shut down their quantum chip project. This decision raised a host of questions, ignited debates, and left many wondering why a company so deeply invested in the future of computing would make such a drastic move. In this video, we're going to dive deep into the reasons behind Microsoft's decision to pull the plug on its quantum chip project. We'll explore the technical and ethical challenges that came with this technology and examine how this shift could shape the future of quantum computing as a whole. As an ethical hacker, I'll show you how this decision is not just about technical feasibility, but also about the far-reaching implications of quantum technology in our world. The rise of quantum computing. Before we get into the specifics of Microsoft's decision, let's first understand why quantum computing has captured the imaginations of scientists and engineers for so long. Quantum computing is based on the principles of quantum mechanics, the fundamental theory in physics that describes nature at the smallest scales, such as that of atoms and subatomic particles. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers process information using quantum bits, or qubits. A qubit is special because it can exist in multiple states at once, thanks to a phenomenon called superposition. This ability allows quantum computers to process vast amounts of data simultaneously, solving problems at speeds that classical computers could only dream of. Additionally, qubits can be entangled, a mind-bending phenomenon where the state of one qubit is directly tied to the state of another, even if they are light years apart. This interconnection can enable faster and more efficient computing, allowing quantum computers to take on complex tasks such as factoring large numbers, simulating molecules for drug discovery, or optimizing global logistics systems. For years, tech companies like IBM, Google, and Microsoft have been racing to build the first truly practical quantum computer. Microsoft, in particular, invested heavily in the field, developing its own unique approach to quantum computing. Their strategy, known as the topological qubit approach, aimed to overcome some of the significant challenges facing quantum computers, such as qubit instability and high error rates. Their vision was to create a stable and scalable quantum computer that could tackle real-world problems. However, despite initial excitement and optimism, it soon became clear that the road ahead for quantum computing was far more complicated than many had initially anticipated. The technical challenges of quantum computing. Building a practical quantum computer has never been easy. The technical obstacles are formidable, and even the most advanced quantum systems today are far from perfect. One of the greatest challenges in quantum computing is decoherence, the process by which quantum information is lost due to interactions with the environment. In classical computing, bits are stable and predictable. But in quantum computing, qubits are fragile and can easily be disturbed by noise, which leads to errors in computation. Researchers have been experimenting with various approaches to stabilize qubits, one of which is the topological qubit, Microsoft's focus. The concept behind topological qubits was brilliant. They are designed to use exotic particles called anyons, which exist in two-dimensional spaces and are resistant to many types of errors that plague other types of qubits. This approach promised to pave the way for more fault-tolerant quantum computing, which is often seen as the holy grail of the field. The problem, however, was that creating and controlling these onions in a lab environment has proven to be incredibly difficult. Despite years of research and substantial investment, Microsoft's topological qubits never materialized as expected. The company faced repeated delays and growing technical challenges. The dream of fault-tolerant quantum computing remained elusive. Moreover, quantum computers require extremely precise environments to operate. They must be kept at near absolute zero temperatures to prevent qubits from interacting with thermal energy, which could disrupt their delicate quantum states. To achieve this, specialized hardware, like dilution refrigerators, is required, adding another layer of complexity and significant cost. Even with these measures, quantum computers are still highly prone to errors. Developing reliable quantum error correction methods has become an ongoing struggle. Microsoft's quantum chip project wasn't immune to these difficulties. Ethical considerations in quantum computing. While the technical hurdles of quantum computing are immense, there are also a host of ethical concerns that come with it, concerns that have only become more pronounced as the technology has evolved. The implications of quantum computing stretch far beyond technical applications. It could fundamentally change the fabric of our digital world. As an ethical hacker, it's crucial to examine the ethical dilemmas that arise with quantum technology, particularly in areas like privacy, security, and the balance of power. Quantum encryption and privacy. One of the most significant ethical concerns surrounding quantum computing is its potential to break current encryption methods. Today's classical encryption algorithms, such as RSA, rely on the assumption that factoring large numbers is incredibly difficult for classical computers. However, quantum computers have the potential to do this in a fraction of the time it would take a classical machine. This means that many of the digital security protocols we rely on today, everything from online banking transactions to email encryption, could be rendered obsolete by quantum computing. This creates a massive ethical dilemma. On the one hand, quantum computing could enhance security through quantum cryptography, which leverages the principles of quantum mechanics to create virtually unbreakable encryption. On the other hand, quantum computers could also be weaponized by malicious actors, governments or corporations, who could use them to break into secure systems and steal sensitive information. This potential for a quantum arms race poses a unique challenge to global digital security. Power dynamics and accessibility. Another important ethical issue is the concentration of power. Quantum computing is an expensive and complex field, requiring specialized expertise and equipment to research and develop. As a result, it's likely that only a small number of powerful corporations or governments will control access to quantum technology in the near future. This raises the critical question, who will control quantum technology, and how will it be used? If quantum computing falls into the hands of a select few, it could exacerbate existing inequalities and further entrench power structures, leaving the broader population at a disadvantage. This would create a digital divide unlike anything we've seen before. As quantum computing evolves, it will be essential to ensure that these technologies are used responsibly and equitably, fostering transparency, fairness, and accountability in their development. Environmental impact. Finally, we must consider the environmental impact of quantum computing. As mentioned, quantum computers need to operate at near absolute zero temperatures, which requires massive energy consumption to maintain cooling systems. This could lead to significant environmental costs, especially as quantum systems become more widespread and large-scale infrastructures are needed to support them. If quantum computers are to become a mainstay in society, developing energy-efficient quantum systems will be crucial to minimizing the carbon footprint of these groundbreaking technologies. Why did Microsoft shut down its quantum chip project? Now, let's return to the central question, why did Microsoft decide to shut down its quantum chip project? The decision likely reflects a combination of technical, ethical, and business challenges. Despite years of investment, the company was unable to overcome the technical barriers that stood in the way of developing a viable quantum chip. The failure to produce stable, scalable topological qubits, combined with the skyrocketing costs and difficulties in quantum computing, led Microsoft to reassess its approach. In addition to the technical challenges, Microsoft likely took into account the ethical implications of continuing to pursue a technology with such vast societal consequences. Quantum computing has the potential to disrupt privacy, security, and global power structures, and Microsoft may have recognized that pushing forward without addressing these concerns could lead to unintended consequences. Looking to the future, though they are shutting down their quantum chip project, Microsoft is not abandoning quantum computing entirely. Instead, the company is shifting focus toward quantum software and cloud-based quantum services. Through its Azure quantum platform, Microsoft aims to provide cloud-based quantum computing resources that allow businesses and researchers to access quantum systems without having to develop the hardware themselves. This shift in focus reflects a broader trend in the industry, where the future of quantum computing may lie more in the software that runs on quantum hardware, rather than the hardware itself. By focusing on quantum software and cloud infrastructure, Microsoft can still play a leading role in the quantum revolution without the direct responsibility of building quantum chips. Conclusion: Microsoft's decision to shut down its quantum chip project is a pivotal moment in the history of quantum computing. It highlights the immense challenges that still lie ahead in developing practical, scalable quantum systems. But it also serves as a reminder that the ethical, societal, and environmental implications of quantum technology are just as important as the technological breakthroughs themselves. As we continue to push the boundaries of what's possible with quantum computing, it will be essential for researchers, companies, and policymakers to carefully consider the broader impact these technologies will have on society. For now, Microsoft's pivot toward quantum software and cloud services may offer a new path forward, but the journey into the quantum future is far from over. It's clear that while the road to